Okay, thank you, and thank you very much for the invitation. So indeed, the title of my talk is Carroll Swiftons, and this is work done in collaboration with these people and reported in that preprint. Now, actually, the title of my talk could have been Carroll tachyons, because I will describe field theories which are Carroll invariant and which allow propagation outside the Carroll light cone. But because they don't seem to have the same instability pathologies as in the Lorentzian case, we prefer to use the word Swiftons rather than tachyons. The energy, for instance, as I will show in models, in specific models, is bounded from below. So there is no instability from that point of view. I should also say that I will consider here only field theories. Particle models with tachyonic behavior are well known, but this is not what I am going to describe here. Okay, so the outline now that I have explained the title, I will first briefly review how to construct, or one way to construct, Carroll invariant field theories in Carroll flat space. I will then give examples of Swiftons. Then I will show how Carroll invariance in fact it implies a much bigger infinite dimensional invariance, which has been called in the context of fractons space-time subsystem symmetry. So symmetry. Then I will discuss the Hamiltonian. And I will in particular show that the energy from many of the models is bounded from below. And I will also discuss the commutation relations between the energy density at different points. It's like related points. And then, so these are the analog of the Dirac-Schwinger commutation relations for the energy densities at different points. But in the Carroll context, they are simpler. And then I will come with conclusions and final comments. Maybe I can use that. Okay, so this is the outline. And I was told to stress that questions are welcome during the talk. So I do stress it. Okay, so let me start with one, in which I will describe one way to construct Carroll invariant field theories using tensor calculus, in fact. So this is rather a trivial thing, but we will see that it will have an immediate consequence, well, that 3 will follow directly from 1. So it's good to review 1. And for that, I will first recall how we construct Lorentz invariant theories in the metric formulation. So I will consider integer spin fields. So we have the metric, the Lorentz metric, -1, 0, 0, 1, which is invertible, which has a non-zero determinant, so equal to 1, in fact. And the way to construct Lorentz invariant theories, we just use tensor calculus. We contract indices with the metric. If we want an action, we need a density, but there is a density. And if we construct a density, an invariant using eta mu nu, we know that automatically that will be invariant under Lorentz transformations that preserve the form of eta mu nu. So for instance, for a scalar field, so I'm just recalling trivial thing, but as we will see, they are important. So make it massless for simplicity. We know that, well, this is a tensorial expression. All the indices are saturated. This is a scalar. This is a density. So I have a good Lagrangian to integrate over this time. And we know that this is Lorentz invariant by construction. I mean, it's invariant under general diffeomorphism if I were to transform also eta mu nu and eta, but because eta mu nu and eta are fixed, are given, are not fields, it will be invariant under diffeomorphisms that preserve eta mu nu, and this is the Poincaré group. Okay, so how do we do the same in Carroll? So what is an invariant structure which is given in Carroll invariant in what is a Carrollian geometric structure? We had a talk before mine which explained that. Well, now we have a degenerate metric, and I will not use the same letter, so I will call it h mu nu. Use the same. So instead of -1, we have 0. But that means that there are null vectors. And of course, if you have a null vector, any multiple of that null vector is also a null vector. Now we make a choice of a specific null vector. So there is one parameter freedom that we fix. And one way to fix it is by giving, because after all, we want to construct action. So I will, and the determinant of the metric being 0, we cannot have a density of weight 1, but then we bring 1, which I will call omega, and which in Carroll coordinates is equal to 1. And we normalize n in such a way that if I take n-1 vectors space-like of volume 1, and the vector nu, they define a space-time volume equal to 1. Okay, so in other words, one way to write this, if I compute the minor of h mu nu, so that will be omega squared. That's the way to normalize n mu. Okay, and so in this flat coordinates, the vector nu would be 1, well, okay, but so we need one extra thing besides h mu nu, because we are killing through the fact that it is singular, so determinant is equal to 0. We need to recover a way to integrate, and so we introduce a density, which is the same thing as giving a normalization of the null vector. Okay, now how do we construct Carroll invariant field series? Well, there is one obvious way to proceed, which is the so-called electric theory. Well, what is the difficulty? A priori, you have to contract indices. And you have derivatives. So for instance, if I consider a scalar field, I have derivatives, and I would like to construct something which is a scalar. Then once I have a scalar, I multiply by omega, which is in this coordinate system equal to 1. So just like in Lorentz coordinates, it was 1 also, minus the determinant of eta is -1. So how do I raise indices? Well, there is no natural way to raise indices because h mu nu is not invertible. So if you indeed, you can see immediately that if you look at the equation, suppose I give you some covector, let me call it theta mu, and I want to see whether it can be, I can raise the index. So I would like to solve that equation. It's clear that in general you will not be able to solve that equation unless m nu mu, theta mu is equal to 0. So you can only have such a relations if theta mu is annihilated by the null vector. That's because of h mu nu being annihilated by the null vector. And then there is an ambiguity in theta nu that I can always add to it a multiple of the null vector, which is annihilated here. Okay, these are elementary things, but at least we know something from here that if I have a covector, I can always, which is orthogonal to, or which annihilates the null. If I have a covector which annihilates the null vector, I can define its norm in an invariant way, because there is an ambiguity here, but that ambiguity is killed when you compute the norm. More generally, if I have answers which are p times variant and which are annihilated on each index by the normal, then this is meaningful. So we have a way to raise indices, but of covariant objects, but only if these covariant objects are transverse to the normal. Okay, this is important to construct Lagrangian because we want to produce scalars which are invariant under the Carroll group. So this being said, well, there are two ways to, well, there are some ways, many ways to construct invariant. As I said, the electric case would correspond to saturate the index here with the normal. So, well, the standard example of a Carroll invariant theory is just 1/2 and mu phi omega squared. And of course, that's, if you write it in coordinates, 1/2 0 phi squared. Okay, so that's one way, but I want to give other examples which are more interesting, and these will actually correspond to Swiftons, as I will explain, and which use this property that if a tensor is transverse, its norm is well defined. On all its indices, its norm is well defined. And that enables us to construct Lagrangians, which mixes at the same time derivatives and spatial derivatives, and so which will allow propagation outside the Carroll light cone, which is a line, as we have been reminded this morning. Okay, so any questions so far? So one example, so this is two examples. One example that I will consider is a two-scalar model. Then I will consider electromagnetism. I have two scalars, one phi, one chi. I can construct the derivatives, of course. And I could consider for each of them an electric term, but I would like to have a term which is more interesting that mixes spatial and time derivatives. Now, one way to produce such a term is to consider first the antisymmetric tensor where I take mu chi minus mu chi mu phi. Okay, that's an antisymmetric tensor. Now, as such, it does not obey that property. A priori, there is no reason for it to obey that property. But if I saturate it once with the normal, let me see how I defines that. That tensor will be transverse by construction because this is antisymmetric. So it's clear that B nu and nu is equal to 0, which means that B nu is well defined. Sorry? Oh, sorry, yes, because it's because, yeah, okay, I'm sorry. There, I was consistent. Yeah, I will try to. The problem is that when one uses many notations in different papers, one does not. It's difficult to remain consistent throughout. Okay, but thank you. Okay, so because it's transverse, it's well. This norm is well defined, and I can consider a Lagrangian, for instance, in which I would have. Well, I will not write omega, but omega is there, but because it's 1, I'm not writing it. So I would have 1/2. And as I said, for each of them, write an electric term. And then I can add that term with some coupling constant. And this will be really an interaction because B nu is quadratic. The square will be quartic. So that's an interaction between the fields phi and chi. And also you can see that if I look at it's only non-vanishing, well, see if it is, if I look at that, because it is equal to 0, only the spatial components are non-zero, and the spatial components will contain one time derivative and one spatial derivative. So I will have the square of an expression which is linear in time derivative and space derivative, so it will be quadratic when I take the square in the time derivatives. So it will contribute to the kinetic term and quadratic, but with a coefficient that is proportional to the spatial gradients. So I have a Lagrangian which will simultaneously contain time derivatives and spatial gradients, and which is by construction Carroll invariant. All indices are saturated in a way that preserves, that respects Carroll invariance. And well, to integrate, I multiply by omega. Okay.
Can one not understand how in the particle model
perhaps we did not look at that. That's possible, yeah. So we immediately looked at field theoretical models, and we wanted to construct a field. That's an interesting question. We did not look at that. Yeah.
Can one use the fact that Carroll dimensions is a subgroup?
Perhaps, yeah. Yes? Well, let me discuss the Hamiltonian and see that it's not so bad. Okay, but before I discuss the Hamiltonian, I want to give another example and then also make a connection with something that actually we did not realize immediately, but that there is a much bigger symmetry than this finite dimensional one. I think one can put a potential. Okay, so yeah. No, it's just that I. Okay. Yeah, it's allowed. It's allowed. I mean, clearly you can, any scalar that you build out of phi and chi, so even a potential is compatible with the symmetry. No. It's just that we looked at that model specifically. Okay. Now this model can be generalized to include more scalars. Then you would construct something which is cubic and contract with one time with a normal. and because it's antisymmetric, it will be automatically transverse, and that can give you some possible Lagrange term in the Lagrangian. I think actually, yeah, probably here there is there is an internal symmetry. Yeah, this is clearly invariant under rotations, internal rotations. Yeah, so you could also impose to the potential to respect that for masses. Yeah, I just want to give examples, and I have only half an hour, so and it's a blackboard talk. So, but I think I believe a lot of things. I mean, that already was pointed out. A lot of things can be done, and we have not done everything. Another example, which is perhaps which is different, which is electromagnetism. Well, by this I mean massless vector field, electromagnetism. Maybe electromagnetism is not the best terminology, but okay. Now, so we have a vector potential, a mu. We construct now, in general, F mu nu is not transverse, but if I compute again F mu nu times the normal, which I should call nu, that will be transverse. And actually, if I take the square of that, this is the electric limit of Maxwell theory. Okay, so one term in the Lagrangian that I can take is minus a quarter, maybe it's a half, I don't know, mu and mu squared, okay. Which is meaningful because it's transverse, right? So the norm is well defined. But I can do something in the sense, I mean, which is motivated somehow by this construction, which is to consider now a tensor, which, I mean, an antisymmetric tensor with more indices. I just take two curvatures. And antisymmetrize. Then once I have an antisymmetric tensor, it's very easy to produce a transverse tensor. I saturate one's index with a normal. I want to keep sign in agreement with the note. So C mu rho sigma mu sigma. That's clearly a transverse object. If I saturate with one more normal, I get 0. So its norm is well defined, so it can be used as a term in the Lagrangian, which means that I could consider as Lagrangian that plus C mu nu rho, C mu nu rho. And again, it's because it's antisymmetric and you have saturated with a normal, one index will necessarily be 0, the other spatial. So it will be a product of electric field and magnetic field that you take square. So it will be like, you would typically generate terms like EB squared or E squared B squared. And clearly you can complicate because, I mean, these are scalars. I could take a function of these scalars. Okay. I could also complicate by a higher power of this. So once we have invariant, we can complicate. And actually, an interesting question that we did not look at is that we know that there exists an electromagnetic, a Carroll invariant electromagnetic theory, which is duality invariant as well. But we did not write it in Lagrangian form, so I think that would be of interest. How to complicate, well, complicate, I don't know, but what function of these invariants should we take to have duality invariance? And there is a solution that we constructed in the Hamiltonian, but we did not yet translate. Okay. Yeah.
Is this conformal Carroll invariant?
Maybe not for any choice of the function, but I guess that in 4 dimensions, so this was also in any number of dimensions, but in 4 dimensions, I would suspect that something like conformal invariance would be preserved for specific choices. Yeah? No, I don't want to put a second vector potential, and we know that the electromagnetic theory with a single vector potential is duality invariant. E squared minus b squared, although it doesn't look like duality invariant, is duality invariant. And we know that duality invariance can be compatible with Carroll, although E and B looks like now very different, but and we would like to write it in manifestly covariant form.
If you had something
Yeah, so you mean with the second potential?
Yeah.
Yeah, I think, yes, then you are opening more possibilities, yeah. Okay, so just to show that basic tensor rules enable you to construct explicit examples of Carroll invariant theories in which are outside the standard either electric limit or magnetic limit, which only allowed propagation along the light cone, which, as you would say, no propagation, nothing moves. Here we can have propagation at velocities strictly greater than c equal to 0, okay, without violating Carroll invariance. Well, as you said, tachyonic theories exist in Lorentz invariant theories, but now I will show that they seem to be better in this case. Okay? And that's why, for psychological reasons, we did not take the term tachyon. Yeah?
The connection among Carroll also is a invariant theory.
Yeah. Yeah. Now, one good thing of this approach is that we will immediately see that 3 holds. Yes, yes. Now, and so I think that although we have not studied that, the relativistic limit is probably pathologic in some sense, and it would be interesting to see how the pathology decouples or disappears or whatever. Okay. Yeah, in taking the limit, which we have not done. But that would be the only way to. Okay, so let me, because that's perhaps not so obvious, that I will show actually that all these Lagrange that I have written have an infinite dimensional symmetry group. And that this is really a consequence of tensor calculus and the degeneracy of this structure.
Also, this can be seen if you consider the particle model.
Okay, now, I guess so. Now, well, actually, people considered recently in the context of Fracton model what they call space-time subsystem symmetries. And I have many names to quote, so probably I will quote none. Oh, no, I have them here. So there is in particular a paper by, what I had taken, yeah. By Bake, Distler, Karsh, Ross, and Sun, where they are interested in these infinite dimensional symmetries, which I will write in a moment, and constructing actions which are invariant under these infinite dimensional group of symmetries. And their motivation comes from Fracton systems, which we know are not really far from Carroll. Okay, so, and the point I want to make is that if you look at, well, it's well known in the Poincaré case that the group of isometries, so the group of coordinate transformations that preserve that structure is finite dimensional. I mean, non-degenerate metrics have only finite dimensional isometry groups. And linearity is automatic. If I work in Cartesian coordinates, I mean, in Minkowskian coordinates, look at the transformations that preserve at mu nu, without imposing linearity to begin with, it will come out from the computation. Now, if you ask the same question, what is the group of diffeomorphism that preserve that degenerate metric and that volume condition? Because this is what this is the analog of that. It turns out, and this was known, I think it's from the very beginning, I believe, that this group is infinite dimensional and given by the following transformation. You can shift time by an arbitrary function of space. Then, of course, you have the standard thing in space. I mean, special metric is not degenerate, so you have the translation and the rotations. Now, it turns out that this group was precisely the group considered by the authors I mentioned, and they call that these symmetries, and they construct actions invariant under these symmetries. They call them space-time subsystem symmetries because these are symmetries exhibited by some subsystems in fractonic models. Okay, but now my claim is that Carroll invariance, if you have a Lagrangian constructed by tensor methods, where you are saturating indices or constructing invariants under Carroll transformations, it will actually be automatically invariant under the group of all symmetries of the Carroll metric, not just the linear ones. Now, if you restrict that to be linear, if you say this is A0 plus BK, let's say, let me, BK xk, then, of course, these would be time translations, these would be the boosts. But from the point of view of the invariance of this structure, linearity is not something that is that is automatic. And actually, you can have nonlinear functions here. So the group of symmetries of that structure is infinite dimensional. And whenever we construct a Lagrangian which is invariant, which is Carroll invariant, it will automatically be invariant under this symmetry group. And so we will have automatically system which is invariant under these subsystem symmetries. And actually, if you look at the Lagrangian that these people constructed, it's exactly the one I wrote somewhere. Well, they wrote it in expanded form because they didn't want to exhibit, I mean, they were not interested in exhibiting Carroll invariance, and this was realized actually later. But if you write this explicitly in space and time components, you will see that you get the Lagrangian exhibit by the people interested in these symmetries. So I think this is one bonus, I believe, of using tensor calculus.
So is that result? This is also valid?
No. If you have a general Carroll structure where this would depend on X, this is what you. So if there is some sort of curvature, then I don't think you would have any isometry at all. This I don't know, in fact. So just like if you take an arbitrary Riemannian metric, there might be no isometry. I'm not sure this is the question. Okay. If I take a curved Carroll structure, it will have the symmetries it has. And I think in some cases, it might just be no isometry.
that this each mu is preserved on the often.
It could be, but so that's okay. Yes, of course, yeah, because that's equivalent to saying that what some people call the extrinsic curvature is equal to zero. Okay, the Lie derivative of that along nu is equal to zero. Yeah, then it's a lot of it's somehow static essentially.
Exactly.
And then you, of course, you would have. I guess this is what you. This would be present. I guess. And the spatial metric can be curved arbitrarily, so this you will lose, but this way I guess will be preserved. In that case.
My question was, if you build your Lagrangian be still invariant under all these towers.
Yeah, because but then you would have to put the h mu nu corresponding to this background which has intrinsic curvature zero. Yeah, I mean. Well, actually, it's if the extrinsic curvature is equal to zero, they are correct. Connections exist. That you have a problem of choice, but there are connections which are without torsion and preserve the structure. It's unnecessary and I mean, what I call it K mu nu because I don't know. So what you call, maybe I even put a 1/2 the derivative of h mu nu. Okay. If this is equal to zero, then you can define parallel transport. And actually, it's really, because when this is equal to zero, you are really taking the product of a three-dimensional of a spatial object with time, and you are just, you can always lift to space-time what you can do in n-1 dimensions. Yeah, because of staticity. And wherever you cut, actually, you get always the same three-dimensional metric. I mean, n-1 dimensional metric. Yes.
You're saying that the Lagrangian is only invariant under more symmetries.
Yeah, but I would think that
It's a subset of the.
Could be, but I would say that which symmetry you get might depend on the Lagrangian. So in that sense, might be accidental symmetries, while these ones will always be present provided you have Carroll invariance. Perhaps, okay. I have not studied the question, so I cannot say. I don't make the claim that I exhaust all symmetries. You see the fact that I have the Euclidean group for a non-degenerate spatial metric, I think strongly suggests that this you cannot enlarge. You might have more here, but it's already not too bad. So I'm not sure. It could be. So I don't want to make a claim. I would suspect, nevertheless, that this would be more accidental symmetries, depending on the choice of Lagrangian, than generic symmetries, valid no matter how you choose your Carroll invariant Lagrangian. But okay, I don't want to make a claim in which I would bet something. Okay. Yes, exactly. Well, I'm not sure that these are exactly, yeah, I think that's an interesting question. How do these match with supertranslations? Supertranslations are related somehow to the conformal Carroll group, and here it's not yet, we are preserving strictly H mu nu. But yeah, it looks very similar. I agree.
For example, there is no in that sense.
Well,
that's not what we call supertranslation. Is the time Yes, these are the superpositions. Because the fact that you have H plus U over 2, just the fact that you are conformal.
Yeah, so I think that the group structure is the same.
Exactly.
How exactly to match, I would think is, I mean, here I'm acting on something, and there we act on data at infinity. There was a matching being done, but at least we have not done it, okay? But I agree that this is an abelian stuff, okay? No, but then I think you would have a bigger group, and where, yeah, that sounds plausible. It has not been done, okay. Exactly,
So you have
yes.
a reduction, so you lose your left is the same.
I think from the Lie algebraic point of view, or the group structure. Okay, other questions? Yes? Very. This one, well, this, but here we are mixing space and time derivatives. Yeah, I think that's an interesting question. So to have I guess the answer is yes, but we would have some. We know that the magnetic formulation is, well, at the same time more tricky and less tricky. I don't know if how you want to put it, but in second order form is slightly more tricky. I don't think. Sorry. Yeah, so the interaction doesn't care about electric or magnetic, so you could change that. Yeah. I think one can probably write more things, and we have not done it, so this would be speculation on good or bad behavior. So maybe let me talk about things we have done. So, as I said, I want to talk about the Hamiltonian simulation. And then there actually is a coupling to gravity in general. And I will only discuss the two scalar model, so this one. So to go to the Hamiltonian, I have to look at where the time derivatives are. So this term contains time derivative, this term contains time derivatives, and here as well there are time derivatives. It's also quadratic with a coefficient which, instead of being constant, will be here a function of the space derivative. So let me rewrite the Lagrangian in a more suggestive form. So it will be quadratic. The Lagrangian is quadratic in time derivatives because I have square of time derivatives here, here, and here, but with a coefficient that will be simple plus complicated. So let me write the coefficient. And I will write it this way. So this would be some kind of, I collect the two scalar fields. So that this is a two-component thing. So there is phi and there is chi, okay, collected. So A takes values 1 and 2. And what is the metric in internal space? It's 1 plus g, spatial derivative of chi squared, minus g, product of, so this is a spatial gradient phi, spatial gradient chi, minus G chi, then 1 plus G squared. We know that in order to go, so if I now compute the conjugate momenta, this is quadratic in time derivative, so I will get this is the conjugate momenta. Well, maybe I can compute. And so I have to invert this metric in internal space to get the Hamiltonian. And so the question is it invertible? What can we say about HAB? Now, actually, it is invertible, and the inverse matrix has a nice expression. So this is 1 over determinant of H, which I will write in a moment, delta AB. And I think this answers the question by Andrea. It looks indeed very much invariant under rotations in internal space. Well, I think at least it can be. Okay, now if you write the determinant explicitly, you find an interesting expression. Well, well, complicated but interesting. D phi squared plus G d chi squared. Maybe I should. And then plus a quadratic term, well, which comes from squared, which is G squared, D phi squared, D chi squared, minus D phi, D chi squared. So you see that, well, if G is positive at least, all terms here are positive or 0. This is strictly positive, actually. This is positive if G is positive. So this is parenthesis. And then this is positive. Now this is also positive because of the triangle inequality. This is the square of the norms minus the square of the scalar product. Okay, so you see that the determinant, when G is positive, and I will make a comment on G negative in a second, when G is positive, the determinant is clearly strictly positive. This is invertible. And the signature, well, because it's a continuous function of G, the signature will be the same as the one for G equal to 0. This is a unit matrix in that case. So clearly it's positive definite. So the Hamiltonian will be, or the Hamiltonian density, the Hamiltonian is obtained by integrating, will just be, I guess, 1/2 inverse HAB by A by B, which will be in the case when G is positive, because HAB is then of Euclidean signature, strictly positive, unless the pi's are 0, but of course that's a... now when G is negative, you can see that there is a competition between this term, which is negative then, this term which is positive, this term which is positive. So you can, and this is important, that for small enough fluctuations, if you look at phi and chi fluctuating around some background, this will be, I mean, the leading order is 1, so that will also be positive. So even for G negative, we can have sensible dynamics if we consider small fluctuations. Okay, but so that, I think, was one of the reasons that convinced us that we should change the name from tachyon to Swiftons, because we have a positive energy. Yeah? Which actually means the same. Huh? I guess we can ask our Greek expert.
Small excitation.
Yeah.
That these particles will carry no energy.
No. well, causality might be a more complicated thing. So I believe that if these particles travel outside the light cone, you can connect things which are not causally connected. So I think causality will be more interesting. Complicated. Yeah, I think so. Which might be actually what was, yeah, so which actually was one of the motivation for considering this, because if you want, for instance, to talk about black holes radiating, what do they radiate and where do they radiate? Okay. How do you measure the temperature and things like that? And we know that they are black holes, as we will hear this afternoon. Also, yeah, also. Excitation, I don't know. Okay. Yeah, but I think that at least you can say that there will be information connecting points which are related by a space-like separation. Okay. So, yeah, okay.
The center of mass in the light cone. Correct. So do not call it information. So it does still comply the naive version of the thing is that if you want to do it with just one, but you have to.
This is a field, and we have two fields. I think it's, we have not looked at that, but I think these are interesting questions.
Yeah, okay, as far as I understood in your paper, there is a field which is the other field is
okay, so one example of solutions to understand the behavior of that is indeed to take one of these two fields as a background with a specific form and to look at perturbations around this background. And indeed, then for the perturbations, you get a Lagrangian with, which can have a hyperbolic propagation character for this perturbation. And of course, you don't see Carroll invariance if you look only at the Lagrangian for the perturbations. But if you remember that this comes with also with a chi, and that when you look at Carroll invariance, chi should also transform. Of course, if I look at this Lagrangian and decide not to transform chi, this is not going to be Carroll invariant. Yeah, so exactly, yeah. But it comes from a Carroll invariant Lagrangian, so there is always well, that's important to keep in mind. So let me finish with one last point, which is, so indeed, well, there was this comment about exact solutions. We alluded to it. I will not say more, but it's indeed interesting to see that when you perturb around backgrounds, either that one or the electromagnetic case as well, you can play the same game of looking at small perturbations. These small perturbations can propagate with a wave operator having hyperbolic character on that background. Okay, now let me just close with one comment, which is, so actually two comments. I would like to, so the Hamiltonian will be, so the generator of time translation will be dn minus 1 times h. Okay? So this is the energy. Now, you can show, and I will say that this actually is not a surprise, if you compute the Poisson bracket, I'm classical, of the energy density at two different points, you get 0. And this is a characteristic property of Carroll. We'll tell you why in a second. But the computation in itself is instructive and interesting. It's not entirely obvious because you see in HAB you have the fields. So when you compute this term at two different points, sorry, where is the Hamilton? Here. So if you didn't have, and you have spatial gradients, and if you didn't have spatial gradients, that would be obvious. But because there are spatial gradients in computation, is not entirely obvious, but can be shown to be true, and it's instructive to carry it explicitly. So you get that. Actually, it's not a surprise. I will tell you in a second why. But as soon as you have this, it's obvious that you can construct an infinite number of conserved quantities. If I look at, let me call that f of f, which is the integral, how did I call it? F of xk. H, well, of course, this also, it's at x, but I want to stress that this is a function. It's clear that this object will commute with the Hamiltonian because of this. And so I have an infinite number of conserved quantities, and the transformations that they generate, which will correspond to that, are precisely the space-time subsystem symmetry. So another way to understand the emergence or the appearance or the presence, whatever, of these space-time subsystem symmetries is to, well, either you like the Hamiltonian, you say that's automatic from the commutation relation here, or the argument I originally gave. But now let me comment on that relation. There is an analogous relation in Poincaré invariant theory that was derived a long time ago in the 60s by Dirac and Schwinger at the time when current algebra were popular, and so they looked at the algebra of the energy momentum tensor components, and in particular at the commutation relations of the energy density at two different points. And I think that one of the papers has titled "The Conditions for a Theory to be Poincaré Invariant" in terms of commutation relations on the component of the energy momentum tensor. And the way they derived it is that by arguing that if it's Poincaré invariant, you can couple it to gravity. We know what is the commutation relations of the gravitation. Oh, I think Dirac did it that way. The gravitational generators of time displacement, and since the algebra, when you put matter, has to remain consistent and first class, the matter energy momentum tensor better behave in a way compatible with the algebra of the Hamiltonian density in the gravitational theory. Now here, it's obvious that we can directly couple this consistently to, we know it's consistent, the coupling to gravity. I just put omega, which might be a function of x. So gravity would have omega of x, h mu nu of x. But all the constructions I have done here, and then the normal would depend on x also. If I multiply by omega, I would have a consistent coupling to gravity. Okay? But I have to take the curved object. But I mean, tensor calculus tell me it's a consistent coupling to gravity, which means that if I go to the Hamiltonian, the consistency condition for coupling to gravity will be fulfilled. And we know that the corresponding gravitational objects commute. Actually, this was perhaps one of the first physical encounter with Carroll structures. You take the gravitational Hamiltonian, take the limit c goes to 0, you get these commutation relations. In a Poincaré, I mean, in Einstein theory, there would be here the component of the momentum density, but it goes away when you take the limit c goes to 0. Now it's clear that now if I couple matter to gravity, I will get as constraint plus the matter part. So let's call it matter now. Okay. And if you want to preserve this algebra for the full object, and you know that the algebra is to be preserved because you have diffeomorphism invariance, the constraint should remain first class. I mean, this would be the constraint. This object here better fulfills this relation. Well, they might be cross-term, but you can show that in in our case where we don't have derivative couplings to the metric, these will be automatically zero in the commutator. So this relation, in a sense, expresses the fact that coupling to gravity is consistent. And then you could take, actually here, either the electric version of gravity or the magnetic version of gravity. Both of them fulfill this. And you will have, now, for matter, I'm not saying anything, but I'm telling you that for gravity, you can take electric or magnetic, and you get a consistent theory in either case. Okay, so I think that my time has come, and so I will stop here.